Hello and welcome. This is Active Inference LiveStream 58.1 on November 7th, 2024. Welcome to the ActInf Institute. We're a participatory online institute that is communicating, learning, and practicing applied active inference. You can find us at links here. This is a recorded and an archived live stream, so please provide feedback so we can improve our work. All backgrounds and perspectives are welcome, and we'll follow video etiquette for live streams. Head over to activeinference.institute to learn more about live streams and other projects. We are in the second in the 58 series. Arun and I last week did 58.0 with some background and context, kind of the approach to scratch the surface. And today we're going to pick it up with Lance, and looking forward to this discussion. So people watching live, please write any live chats. Arun has also prepared a bunch of questions. Let's begin though with Lance, if you want to say hi and welcome back. And then any overviews or any introductions, anything that you feel will help set the table for today. Thank you.
Well, thank you so much. And thank you so much for having me. So, yeah, I'm super excited about this discussion, and I feel a lot of us are trying to understand renormalizing generative models. So I'm sure I'm going to learn a lot as well. Yeah, so just to give a little bit of background. So now Karl Friston is the Chief Scientific Officer at Verses. And one of the challenges that we are kind of like moving towards, and this is public information, is of course scaling active inference. And there's one particular challenge that we're looking at. It's Atari. So for those who don't know, Atari is just a suite of like about 31 games. They've been around for a long time, maybe since the 80s, or I don't know exactly. It's a famous benchmark for reinforcement learning. Now, there's been a lot of work in RL solving Atari, and maybe stuff even like 10 years old already that solves Atari. So the question is, why are we trying to do that with active inference? And the answer is all of these RL methods, they use a lot of data. They're super data hungry, and they're not, so they don't have this human level efficiency that we're looking for. And so that's where active inference could potentially come into play. So one of the things that we're looking at the company is scaling active inference to show that we can solve Atari with a human level efficiency. And so this scale-free approach, planning from pixels, emerged out of these efforts. And this has been work led by Karl. So he's come up with the ideas and the code and so forth. And so now we're still pushing with this approach and other approaches. So yeah, it's super exciting, and there's many research questions of things we could explore. So very excited to discuss it today.
Okay. Do you want to give any connective tissue between some of your previous conversations or papers or streams? And then we'll jump into the listed questions we have.
Sure. So for those who don't know me, so I'm Lance. I've been working on the Trinity principle active inference for a long time, primarily on the mathematical side of things. So back when I started, possibly the only person understanding active inference was Karl himself, and a few privileged people around Karl. And so a lot of the work I did was to try to understand things and put them on a more rigorous mathematical footing. And so we've had a few conversations here, a few live streams speaking about some of that. So I would say the RGM work that we're discussing today is a bit different from what I've been working so far. So previous work was mostly on the theory of the Trinity principle, theory of active inference, to read the math. Today it's more about a piece of code that does things, and it does really cool things. Also has some interesting limitations, and so it's a much more pragmatic agenda. And I'm personally moving in this more pragmatic set of things, but I have a lot to learn. Yeah, so this is how things stand at the moment.
Yes, it was LiveStream 52 on the geometric methods for sampling, optimization, inference, and adaptive agents. That was a great and very epistemic setting. And then also, now that I'm seeing it, also 26. So it was sort of a 2652 full card Lance situation. But both of these were some of the clearest and most fundamental papers and unpackings in the series. Arun, anything you want to begin with, or we can just jump into the questions you wrote?
I mean, first of all, just to say, like, I need to catch up on those because those sound great. Also, I think some of my questions are still fairly, like, don't want to say like towards the end of the paper. They're much more like discussion points, but I don't know if maybe for some people who might not have been able to catch the first session, to maybe go into a very high level summary of the paper first, and then set some background, and that might make the discussion points a bit clearer as they happen. But very happy for you to take the lead on that one, Daniel.
Yeah, Lance, what would you say is the overall summary through line, and then we'll turn to the specific questions.
Sure. So should I give a quick summary? Or? Yeah.
Yeah.
Right. So, yeah. So the problem that we're looking at is planning from pixels. So you have a bunch of pixels, and we want to, do decision making. So for those who are familiar with active inference, there's typically two flavors of active inference. There's the reflexive type of active inference where you're not really planning in the future, but you're like, if I infer that I'm in this state, then I should do this, and if I infer I'm in this state, I should do that. And that's typically what we see in continuous active inference. And then there's the other flavor of active inference and also sophisticated inference, which is typically in discrete states. And that has planning, that has expected free energy, it has exploration, and so forth. Here we are in a setting where we are doing things in discrete states, but we are reflexive. So this is just to situate with the other things that are in the literature. And so what happens is we get a bunch of pixels. So yeah, just to go back a little bit, this is the pixels for planning paper is a way to learn from expert data. So if I look at expert data of an agent doing something, I'm going to be able to learn that with an RGM and reproduce it in some kind of a habitual reflexive loop. But I'm not going to do any kind of de novo learning. And so then there's like a very specific architecture for the RGM generative model that allows it to do what it does. And there's a way we can, learn these things. But that's kind of like the broad idea, or at least the context.
Okay, awesome. Yeah, just we have the figures if there's any to jump to. Let's go to the first question. So, how are renormalizability and sparsity linked? And also if you could connect that to how else we've seen sparsity discussed in the Markov blanket concept. What's sparsity in a graphical model? How is renormalizability doing something similar or different than the sparsity conditions that we've studied before?
Right. Yeah, just to give a bit of context on that question, because you talked about Markov blankets. So Karl and a number of people have this idea that living systems, and I guess systems in general, are made of Markov blankets. I mean, they're themselves Markov blankets. And so if you take an organism, it would be composed, for example, of organs with their own Markov blankets are themselves made of cells with their own Markov blankets. And you can, subdivide many times, sort of zoom in, and you'll still see Markov blankets everywhere. And so what you get from that, or probably what Karl got from that, is that there is some kind of scale-free invariance about the nature of things, which is that if you zoom in or if you zoom out and arbitrary zooming or de-zooming, you would still have this kind of like fundamental structure. And I should say the renormalisation group is a mathematical apparatus for zooming in or zooming out on things. And so basically these renormalising generative models, they have this assumption that the world is renormalizable, that the world has some kind of a scale-free information within them. And so we can get more into the details of that, but basically, long story short, is that this renormalization aspect, it gives you a very powerful inductive bias on the structure of your generative model. And in this case, it gives you this kind of renormalizing generative model, which is a generative model that looks the same at every scale. So it's a generative model that if you give it pixel data that's sort of very zoomed in, that part of the model that feeds that data is going to be the same in terms of its structure than the high level parts of the model that look at like much more coarse-grained features. And these models are very sparse. Just because when you look at the representations in the model, there's many connections that are missing, but by design, on purpose, right? So we have a lot of sparsity. So it means that they're very lightweight. And I would say that's kind of the main advantage, right? So when we compare with traditional machine learning architectures, and this is not to say that this approach has a lot of limitations, but one of the strengths is that we get some very lightweight models that can learn things with a relatively low number of states, and I think that goes back to sparsity.
Okay, let's look at the figure and talk about the architecture. Maybe continue a little bit on what specifically how can we see that renormalization structure in figure 3, and how does this have similarity and differences than like the textbook generative models that we've worked with?
Right. So I should say, full disclaimer, I don't think the explanation of renormalizing generative models is very clear in the paper. And some will say it's extremely unclear. So I'm going to try to clear some of that confusion. But there's also a part of it where I'm probably still confused. So apologies in advance if I cannot clear all the confusion. But so I can try to describe the figure that you have here, and then I can also give you my own kind of personal summary of generative models, of renormalizing generative models. So here we have kind of a classic hierarchical, partially observed Markov decision process. And the special features is that there's a time horizon of 1 at each layer. And then you have this renormalizing scale-free aspect, where, as you can see at the bottom level, you have 2 states, 2 actions. These are grouped into 1 state, 1 action at the level above. And then if you go 1 level even further above, there's again 2 states at the level below and 2 actions that are grouped into 1 state and 1 action at the level above. And you can go like that for as many layers as you want. in the current code, what you do is you specify the number of layers that you want to start with, and then you would kind of learn, the transition mappings and so on and so forth.
What aspects of the code are available, or what languages or timeline for overall applying it?
You mean for applying it in, to machine learning tests? Is it?
Or just for any of these settings, what is the code availability, or what do you think are the promising ways today and going forward for people who are interested in the open source active inference implementations to work with it?
Right. Yeah. So I'm not entirely sure as to the kind of like privacy constraints on the code right now. I would assume there's a link in the paper pointing to a repo, but if that's not the case, it's not the case. Okay. Well, so I know it's on a private version of SPM, and so if it hasn't been released yet, then there's surely talks inside the company of like when to release it, how to release it. Yes, I'm not exactly sure about the timeline of that, unfortunately.
Okay, all good. Yeah, I mean it's an interesting meta piece with the research and being able to share that, and with this information here from the pseudocode, it gives a lot of the recipe and the anatomy of the model. But let me just is there another part of this figure or another figure to continue specifying a little bit more about what's happening, or do we want to jump back to the questions?
Yeah, so there's a presentation by Tim Verbelen that I'm and there's a useful slide on that presentation that I could potentially show. I don't know if I can share my screen here, but I think it would be quite useful to illustrate a bit more in detail what's going on.
Oh yeah, share your screen and
so let's see if I can do that. This is on your computer. Okay. Yeah, unfortunately, I'm not going to be able to do it because it's. I mean, I could, but I need to fiddle with the settings.
Or you could email it.
And I don't have admin rates.
Okay, you could email any slides if you wanted to admin.
Yeah, I'll check and I'll get back to you on that. But I'm happy to explain.
Yeah, continue.
What I was going to show. So the idea, and here I'm going to have to wave my hands a bit, but hopefully it's clear. So you get some pixel data, you get a movie. But basically, that's what our RGMs do. You get a movie of an agent doing something, and you're going to learn a generative model that learns that and is able to reproduce the agent in the movie. And so it's able to learn its actions and reproduce its actions depending on the state. So the way it works is you take one frame of the movie and you take the next frame, and this would be like your low-level observation for the renormalising generative model. So why do we take two consecutive frames as one observation? It's because we want to extract position but also momentum information. So that's our observation, two consecutive frames. Then each frame we're gonna divide it into several overlapping patches. So just like a convolutional neural network would. So you have like multiple patches that overlap, each centered, for example, around pixel. And then each of those patches, you do a singular value decomposition, which is that you take the eigenvectors. So you have those pixel vectors, you take the eigenvectors, and you essentially do a PCA. And the reason why you do that, so just to give a little bit of context. Well, first of all, planning is much easier in discrete states. So somehow things work a lot better, or it seems, or at least that's what we think at this moment. So we want to convert this kind of like very high dimensional kind of continuous data that are pixels into some more manageable size, low dimensional discrete representation that we can then work with in the RGM. And so there's potentially many ways you could do that. And one way would be to use like kind of for example, a variational autoencoder, where you would then discretize the latent space. That would be one way to get from continuous to discrete. So there's many ways you can do this step. The reason why I suppose Karl chose SVD is because it's very lightweight, and it's also very, I would say, context sensitive. So if you give one bit of data, it will adapt to that data. If you give it another bit of data, it will adapt as well. There's arguably also pros to using a deep learning architecture. The cons is that it would need to be trained. So lots to explore there. But for now, we use SVD. And so, so once you've done your singular value decomposition, you get these eigenvectors that you still get a list of eigenvectors for each patch that tell you, okay, well, this is like the most important feature in the patch of pixel. This is the second most important feature, third most important feature, and so forth. What you do is you truncate that. So you take the most important features and then you discretize that. So it's a lot of steps. I know, so hopefully I can send you a picture. But the point is that you extract the features using SVD, so you get a much lower dimensional representation of the data. And because you truncate it, you kind of eliminate the noise, you eliminate the things you don't care. And then this low dimensional thing, which is still continuous because these are eigenvectors, you can discretize it using multiple bins. So now you have discrete data. And once you have your discrete data, then you can fit it to the picture that you have in the slide right there and do your hierarchical NDP, kind of like much more classic.
Yeah, awesome. Yeah, in the .0, we talked a little bit about that process, about going from the continuous to the discrete to enable planning over the discretized form. Arun, go for it.
Yeah, I mean, thanks for that summary, Lars. It was really clear and informative. One question I have just to follow up on that is when something you said quite early on, which is that planning in the continuous space is really difficult. Could you say a little bit about why that is? So the reason I ask is I think it's a very common thing that people would want to do is have an agent that can plan an action to do this thing, but control the degree at which it does it. So I would like to move, but by a certain amount. How do I choose how much to move in a continuous distance? So I guess maybe could you say a little bit about why it's so difficult to plan in continuous space?
It's a really good question. So I think, so planning is always about doing things. So when I talk about planning, I don't talk specifically about action selection. I talk about imagining what will happen, in a certain time interval in the future. So it means that you're looking at what would happen if I did that in terms of what is the trajectory of what would happen if I did that. Now, if you're in discrete space, discrete time, you're looking at a sequence of future states. But if you're in, and so your space of trajectories that you're kind of like planning over is discrete, because it's like possible steps at the next time step and then 10 possible steps at the next time step. So it can be huge, but it's discrete. When you're in continuous space, if you want to plan in a certain time interval in the future, you're looking at trajectories of what would happen if you took a particular trajectory of actions. And so if you're in continuous space, continuous time, the space of trajectories is infinite dimensional. So I think that's kind of like it's infinite and it's also infinite dimensional. So it's kind of like really bad. And yeah, and there's probably, I mean, there are algorithms that kind of do this. I'm not really an expert on that, but I think that's kind of like the underlying limitation, the fundamental mathematical limitation. And so the thing you can do then to plan in continuous space, continuous time is you abstract away on a discrete space, and then you go back down. And this is what we've been doing. I mean, as you know, in active inference, it's kind of like the hack. There's probably other ways to do it, but yeah, that's where we're at.
So maybe something just to clarify there is the nature of these infinities, right? So you said infinite dimensional, but then also it's almost like infinite values for each of those dimensions. So that's why it gets really explosive in the number of things you have to consider. One of the things that we talked about in the .0 was the path-based formulation and how that seemed to be even more combinations you would have to consider compared to the textbook formulation, where now we're considering paths over states and actions, and there are as many combinations of paths of like combining states and action choices, which already sounded like quite difficult to solve relative to sort of the toy examples of just what's in the book. So maybe you could say a little bit about that.
Right. So just to make sure I'm on the same page with you, what do you mean exactly by the path-based formulation?
So I think it's when we're now
just figure 4.3 from the textbook is kind of a good touch point. On the top is the discrete time, explicit states and observations at time points are considered. Time point 1, 2, 3, 4. In a continuous time, future time points are only predicted through a Taylor series generalized coordinates expansion, which is something we talked about in 52. Or continue from there. Just wanted to bring in those two textbook figures and how they can be combined in a hybrid architecture that kind of presages what we're talking about today.
Yeah. Okay. It's interesting that you bring up generalized coordinates because when I was mentioning myopic active inference or like not using paths, I wasn't specifically referring to generalized coordinates, kind of like the more simpler version without the generalized coordinates. Because you're right, you're absolutely right that when you have generalized coordinates, you do get trajectories again. The difference or one of the differences is in discrete states, you may have a limited computational budget that kind of limits you in several ways, but at least theoretically you can plan infinitely or arbitrarily far ahead in the future, even though your beliefs would get very imprecise. In continuous states, when you have generalized coordinates, you have this notion of encoding implicit trajectories in the future through these Taylor expansions, but the Taylor expansions are only, by design, only going to be accurate on a very small or small time interval. So already theoretically, if you have only finitely many generalized coordinates, which is what you always have in practice, you're now able to plan very far in the future. But I agree, this is like much more sophisticated than any kind of active inference without the generalized coordinates or the things that I was mentioning before. One other thing is so when you do planning in discrete states, you're like comparing multiple trajectories of actions. If I remember right, but correct me here if I'm wrong. When you do planning in the continuous states with generalized coordinates, so at the bottom of 4.3, you're always minimizing the gradient of the free energy with your actions. So even though you plan the trajectories of states in the future, if you did that, you don't plan for sequences of actions.
I believe that that's true, or another way to say that is that the continuous time formalization, even if you do have a high degree Taylor series expansion or a lot of generalized coordinates, it isn't explicitly considering counterfactual scenarios. Like tree search in chess, it's like 7 moves down the road. If 1, 2, 3, 4, 5, 6, 7, then 8A, 8B, 8C. Whereas in a continuous time expansion, you get one polynomial approximator, but it isn't saying, well, what if time point 12 were different? All you could say is something about the statistics of that path as interpolated, but you wouldn't be able to directly make strong guarantees outside of following the gradients around that inferred path.
So maybe I've mistaken something, but either in one of the points that you've written there, Daniel, or something Lance said, I remember the word reflexive for the continuous time active inference. Is that what we're saying here? Is that yeah, there we go. Without planning, at least with the continuous time formulation, yes, it's sort of doing something with the expectation of what's going to happen in the future. But as you say, it's not considering counterfactuals. We're not considering if I do this, then this. If I go 10 meters rather than 20 meters, this will happen, etc.
Yeah. Yeah, I think it would be interesting if you ask that question to Karl, if he draws the same distinction, but I would totally agree with you. I would say so. At the beginning, I was referring to continuous active inference without the generalized coordinates as being reflexive. I would say that with generalized coordinates, it's still reflexive, but you're right that it's already much more sophisticated in a sense.
Yeah, the generalized coordinates are like a way to bring the depth in. It's like doing momentum trading on a stock over multiple timescales. You're still making an instantaneous decision in the sense you're looking at a vector of the current moment and then looking at different trends and first, second, third, etc., higher moments. However, again, there's not explicit planning. So this sort of gets into the functional underpinnings of anticipatory behavior and whether anticipatory behavior can be loaded up into a sort of reflexive, intuitive moment, or to what extent it involves explicit tree-based search of branching possibilities.
Yeah, totally.
Okay, but just to close the loop on the sparsity, could we say generative models are defined by their sparsity? We're literally talking about some set of random variables, nodes, and their edges, which defines their sparsity conditions. Any node interpolating between two other nodes is a blanket. People often are interested in the agent environment blanket as interface. However, taking the graphical model as a Bayes graph itself, we can think about the B matrix here as being a blanket, for example, between these other two nodes. The sparsity conditions of figure 3 and whatever model you design, the connectivity is the sparsity condition. Renormalisation generative models have a special template or recipe for how the sparsity conditions are related within and across levels. Okay. Arun, want to pick one of these or which one to go to next?
I actually think the next one they're sort of roughly in an order. So yeah, I think talking about the RG operators, because it is the really new thing in this paper, what makes a good one?
What makes a good RG operator? So, yeah, I mean, I'm assuming if you ask this question, you probably know more about RG operators than I do. So it'd be interesting to know what you think about this. Yeah, to be honest, like, yeah, just to give like a comment. This is one of the things that I really need to read up on. Karl repeatedly says there is this universal aspect to renormalizing giant models. And I agree that there is some part of nature that seems to be scale-free in terms of like these Markov blankets at different scales. But to me, there is also a lot of nature that is not scale-free. I mean, not everything that you look at is a fractal. So in what sense are RGMs universal? The super cool thing and surprising thing for me in this paper is that there's a lot of things that you can do with RGMs. There's a lot of things that you can learn. And I'm not sure to what extent. I mean, I would really like to know, okay, well, this is one thing that you cannot do with RGMs in terms of like, I cannot memorize this. Yeah, that's something I'm not sure about.
So maybe I can sort of come back on that. So I think the use of the SVD and effectively principal components analysis in this paper is actually like a really nice introduction to renormalization groups if you don't know if you haven't heard of them before. It's very common in other aspects of more like traditional pattern matching and machine learning. And there's loads of good tutorials just out on the web. We've got a couple linked in the slides to explain what it does. So I think just saying, like, to summarize that very quickly, PCA is you do a transformation on your data to maximize variance amongst particular dimensions, and then you can do a dimensionality reduction by throwing away the dimensions you don't want. So that really neatly leads into the definition of RGMs in this paper, which is the coarse graining. It's the critical part is that you are throwing bits away that you think aren't important at particular levels. And then as you go up levels, you throw away different dimensions, but they feed into the lower levels. But I think there's also a lot of talk in this paper about like the spin block transformation as well, of how the pixels are sort of blocked up, and then you say, okay, we're going to coarse grain in space, and also coarse graining in time. That's in a couple of the examples in the paper as well. But I guess my sort of question is particularly on the, like, how do we know our coarse graining is not throwing away actually useful information? And how does that relate to the data that we're putting into the training as well? I think that's because I know you mentioned before this is all about learning from expert play. Mm-hmm. But are we also possibly throwing away some of the expertise when we coarse grain?
Totally. Yeah, totally. I mean, as far as things stand at the moment, this is more of an open question, research question. So some of the things that we're doing is, testing RGMs on different kinds of expert play for different games or for different environments in and outside of Atari, and looking at how well it works. So my own take right now is that RGMs are pretty good at memorizing really a bunch of things, a bunch of expert play. Two things. For RGMs to do well, the game or the environment needs to have some kind of orbits, some kind of orbit structure that the RGM would learn. So that's like one thing that's pretty important. The main challenge of RGMs that we've kind of been looking at or looking into is generalizability. So one of the things that we show in the paper, which is pretty cool, I think, is this Dove example. So we learn this Dove video with the RGM, and then we occlude the Dove, and the RGM is able to infer, so it's going back to its training data, its reconstruction of the training data, and reconstructing the Dove. So that's one type of generalization that works very well. But it kind of highlights perhaps, what seems to be a drawback as well. So the RGM learns representations of the training data, which means that when you expose it to non-training data, such as the Dove, which is occluded, it will go back to training data and be like, okay, well, this is the Dove that I saw in my training, and so I'm going to reconstruct it. what if you train it on expert play for a game or expert something for something, and then you initialize the RGM at a different condition. So let's say let's say you train the RGM on walking data, some robot walking. The RGM will learn the orbits of walking, and it will be able to reconstruct the motion and the actions of walking. But now if you initialize the RGM of like, I'm lying flat on the ground, it won't be able to stand up to go back on the walking orbit. It will infer that it's walking, and it would execute the actions of walking even though it's flat on the ground. So you can imagine the motion that you get out of it. And this is a kind of a generalization aspect where RGMs are really lacking. Is if you're outside of the training data, you're going to infer that you're in your training data when in fact that you're not. How do you go back to the things that you learn? How do you pick up the orbit?
Yeah.
This definitely came up in the previous one, the 0.0 as well, Daniel. We're talking about resiliency of models. And this is, I think, a really interesting question of, how do you know if you're out of distribution? Mm-hmm. If you, like, there are other sort of machine learning applications of maybe like kernel density estimation or whatever, where you might say, okay, I've trained on this data, I get this new data, can I compare it to a probability distribution and say, oh, wait, this doesn't look like anything else that I've seen before. I'm now very uncertain on what to do. Is there a way we could apply those sorts of principles here?
Yeah, I suppose so. So this would be a very interesting project because, I mean, this is the main limitation with RGMs right now. And there's possibly many routes forward, but at the moment, that's the main challenge. So taking inspiration from the things that you mentioned would be super promising.
One way that active inference models at least have a diagnostic is surprise bounded by variational free energy does give you a measure of overall how likely something is apt to be. So if you have a training on driving safely, then you're minimally surprised by the safe drive. You have a measure, at least, this kind of threat agnostic measure of something different is happening. However, it's almost a general information theory problem of, well, the space of what you don't know is always going to be so much larger. There's always more that you could be surprised by. Like, for all the combinations of valid English sentences that language models are trained on, there are more combinations of gibberish sequences. So then, how to make something that can weave its way back into the orbital zone or into a zone of control, and that's where some of the multi-scale architectures and switching architectures come into play, because the variational free energy value itself isn't going to say what to do when the car is off-road, but at least it would be a diagnostic of how, like a kernel density estimator, how similar it is to training information.
Just another thing to bring in as well. I think we're sort of bringing all the questions in at once, but it's all related and it's all relevant. The question of how, if we are only training these things on expert play, how can we create resilient agents that can recover from unseen positions to, so quote unquote, get back on the path? So I think one of the things that came to my mind when I was reading the paper was, if you give it data where it starts off in a losing position, and you can show it ways of going, if you are losing, this is how you get to winning, then that would become a new potential attractor set that, okay, if I am losing, I can then move to another sets where I'm winning. So you explicitly give it that journey as data that it sees. But then I think we come on to one of my other questions, which is, how do we then tell an agent that has learn the structure from the data itself, which attractor sets are good and which are bad? How do we inject value into these to say, okay, we've given you this data where, let's say, the self-driving car is a really nice example. Driving safely is great. If you are in an accident and you drive off-road, this is how you get back onto the path. But if it's learned the structure of those actions from the data itself, how do we then inject the value that actually driving safely is good and being off-road is bad?
Yeah, I mean, really interesting questions. So I have a few thoughts that I think echo what you said, and I don't have specific solutions, but just to echo what you said. So, for example, in the case of walking, we might ask, okay, well, if we have the training data for a walking agent, and somehow the agent is like down, either sitting or lying down, we should teach it how to stand up. And then once it's recovered its starting position, it can go back and use the RGM policy. So that's one solution. Going back to the starting point of the orbit that works. But there are challenges. So for example, and this is maybe a slightly different challenge, but also coming back to self-driving cars. A self-driving car is a very, very high dimensional system, lots of moving parts, actions, things that are going on. So if you give the RGM a lot of driving data of driving safely, I'm assuming the RGM would learn it profitably. But now if you expose it to a new situation it hasn't seen before in the training set, and I would assume this would just happen very easily, right? Because we're such in a very, very high dimensional space. I mean, when you think about it, it's kind of a curse of dimensionality problem, because you're feeding trajectories to the RGM. So trajectories or orbits, these are one-dimensional objects, and you're in a state space that could be very high dimensional. For example, in a self-driving car, and what you want is to get full coverage of like the underlying manifold of safe driving. And what you also want is, if you're in an unsafe driving situation, you want the trajectory that gets you back to the manifold of self-driving. So you have these two problems. So one problem, coming back to the curse of dimensionality, is that if you have this extremely high dimensional manifold of safe driving, you want to cover it with one-dimensional trajectories. The higher the dimension, the harder it's going to be, because you're trying to cover a large n-dimensional thing with one-dimensional objects. So computationally, it's going to be a problem. So there's this generalization that doesn't work, like within, as you said, like within data distribution generalization, that's a problem. Because if you give it a lot of data of the driving safely situation, we would want it to kind of extrapolate over all safe scenarios of driving. And we don't really see that at the moment, or at least maybe it happens, but it could be a challenge in some situations. And the other one, which is maybe the more fundamental problem, is you have this huge region of driving not safely. How do you go back to the driving safely situation? Also coming back to the example of walking, how does that happen? And that's also very hard, right? Because potentially we would want to, have a trajectory back to the safe situation from every possible starting location. But as the state space becomes very large, that also becomes very difficult.
Yeah. When thinking about all the angles your joints could be in, all the muscle energies, there might be a very small zone. So how to really think about adaptive active inference agents at the agentic level, and then also more at the systems design level, how could components be robust and adaptive and simplified components doing better on a subtask, and then design a composed system where the sort of low energy, efficacious operation of the smaller units is designed in a way where they are not dealing with that massive overall computational challenge. They're dealing with local computational challenges. However, that moves the design challenge to or moves the functional challenge to design time rather than inference time. But most morphologies don't walk. But if you have one that walks through evolution or whatnot, then it may be a relatively simplified inference problem at runtime. However, the challenge is basically figuring out which of those sparsities and message passing schemes would result in tractable node level inference. Otherwise, it would be hard to do on a relevant hardware.
And adding to that, if I may, so going back to the walking example that you mentioned, and also the generalizing within data distribution. So there is evidence, and that's also something that we've kind of encountered empirically, that walking is a chaotic orbit, which means that if you, so let's say I'm here and I'm going to take some actions and I walk. Now, let's say I start from a slightly different, infinitesimally different initial condition, and I take the exact same actions, I'm going to fall at some point. And that's like the chaoticity, right? So if you take the same actions, but you start from a different initial condition, you're going to diverge very far away at some point. And so we have, and I think we have this problem in RGMs that if we teach the agent to go back to the standing position and then take the RGM policy, if the agent has a slightly different initial condition than what the RGM was trained on, the RGM will infer that it is in the true starting position, even though it's slightly different. And then it will take the actions of the RGM and it will fall at some point. So you have this idea that just memorizing just doesn't work in that situation. And yeah, that's also an issue.
So maybe just a small question there. Is the issue there that with the coarse graining part, in that a slight change in initial conditions is being thrown away by the PCA and throwing away dimensions early on, and then when we go back and do the inference, we infer that we are sort of in quote unquote the same place because we've thrown away like something that is actually signal has gone to the noise part of this.
Yeah, I imagine that's one way to look at it. The way I've been looking at it, but I haven't been thinking about it in those terms, is just if your training data is one particular orbit trajectory and you start slightly different, because you're inferring where you are based on the training data, based on the structure that you've learned, you're going to infer that you're on your right trajectory, even though you're not, and you're going to reproduce that, but you're going to land arbitrarily far. But yeah, I assume it's the same phenomenon.
This kind of gets to the whole structure determination question. Chaotic systems are sensitive to small changes near critical points, but then there might be another zone of the system that isn't so susceptible to critical points. So like, let's look at the chaotic attractor example from the paper in figure 13. If we were to make a small change while we were out on one of the arms of the attractor, it might not change things that much. But then there might be some other points where it does lead to taking a bifurcation. So if you can break up systems so that the coarse graining captures those bifurcations into two discrete categories, then it discretizes a continuous chaotic system well. But then if you are applying a grid that's incommensurate with what's actually happening, then any grid you draw is going to include trajectories that have radically different outcomes. So the overall predictive efficacy or the variance retention of the SVD is going to be low. Like if there's actually two zones in a city and they're 1 mile squared and they have different properties, and you have a 1 mile grid and you actually capture it, you carve nature at the joints or articulate it at the joints. But if every block has mixed zoning and all you have is a 1 mile grid, you could do the best placement of your 1 mile grid, but it still is always going to capture something that's kind of mixed. And this kind of related to a few of our thoughts and questions, like how do we determine what window to use just from a generic perspective? Like there was 10 levels in the discretization of a grayscale image, or there was a 4x4, or the MNIST images were pre-processed to 32 by 32 pixels, and then they were blocked in 4x4 grids. So how much sweeping, or how do you do inference on the number of discretizations and the window size and all these other features? Like what kinds of trade-offs computationally do you look for, or how many levels of meta modeling do you feel like are relevant to engage in when you could sweep across discretization of N and windows of M, and then you could have, well, window size of 6 with a discretization of 3 gives this performance, but something. So how to even navigate through that combinatorics?
Yeah, really good question. So, yeah, at the moment it's very much, because this is very much a new thing, for the moment these are hyperparameters, and we're very much in the exploratory phase of, okay, well, this works and this doesn't work. I mean, I'm assuming I'm thinking for the paper there wasn't much hyperparameter tuning, like it was all, powers of 2 that were chosen and a small number of layers. But when you think about it, I mean, you could do renormalization by powers of 3, powers of 4. You could choose to have smaller or bigger patches, increase or decrease the number of patches. So there's many things you can be looking at. And I would say that's also a problem that you would get if you were to do structured learning with generative models that are not specifically renormalizing generative models. You also have that problem of, okay, how many patches, how many layers, and so forth. So this is not a problem that's like specific to this approach. What this approach has, which makes the problem a lot easier, is that there is a lot of interplay between the number of layers and the number of patches, right? So if you choose, I'm gonna renormalize by 2, so it means that 2 states at one level become 1 state at the next level, and 2 states at that level become 1 state at the next level. This gives you a relationship between the number of states and the number of layers that you have, and also implicitly the number of patches that you have. So you have this like big constraint that comes in renormalizing generative models that makes the search a lot simpler than otherwise. But I think ultimately, what you would probably want is to infer, and I think we hinted at that, infer like the number of patches and so forth. Yeah, we're not doing that. It would be cool to do that.
I think another possible thing we could try is maybe start with a budget of this many layers, patches, like basically combinatorics, and set, okay, you have this much computational power for understanding this data. Figure out the best way of allocating that, because at some levels you might have more variability than others, and maybe you want to allocate your computational budget at the higher abstract levels than you do, more so than you want to do at the pixel level. And perhaps we could learn that from the data itself, given a constraint of this many parameters. And I think you could probably code that up multiple ways, but one way you could have priors on those hyperparameters, and then I think, as Daniel suggested in the point zero, do a free energy calculation on that compared to that, your priors on those hyperparameters, and just minimize free energy that way. But you could also probably do a hacky approach as well, and just go, well, what gives me the best performance? Call it there.
Mm. Yeah, and just to kind of echo that and complement that. So as you both mentioned, the issue is, well, there's so many hyperparameters. I mean, there's so many quote unquote, right? Because if we're using generative models that we're not renormalizing, there would be even more of them. But even here, we have a lot of hyperparameters, and so that's a separate thing that we're also working on, but which is, can we infer the structure of the model instead of just saying, oh well, we have this data, this is the model that we get. I think we need to be recognizing the fact that with limited data, you're always going to be unsure about the resulting model, and so we need to have probability distributions over models. And so one instance of that is what you mentioned, like we have probability distribution a prior over the number of patches, and we optimize that with respect to free energy. But we could also have probability distributions over 3 layers or 4 layers, and so forth. And I think this is where this is kind of, beyond this paper, but where we need to be going is having uncertainty about the model. And so then if I have uncertainty about the model, I can take actions upon the world that maximize the expected information gain about the model. So then I'm going to get data that's maximally informative to refine my beliefs, ultimately converging about the best model of the world, or maybe a set of candidate bests, if there is a fundamental obstruction where you cannot find which one fits best. But the point is, in this approach to structured learning, and I think in every other approach that we have in active inference so far, we're not recognizing the inherent uncertainty about the model. And so what we're doing in the in all these structured learning approaches is a kind of well, imagine if you have a prior over models. Then if you have data, you have implicitly a posterior over models. Now, this is what I think we need to do, and what we're currently doing implicitly by taking the model with the lowest free energy, when we actually do that, is taking a flat prior over models and then taking the most likely model in the posterior. So we're doing this maximum a posteriori estimation when we're optimizing model free energy. And yeah, ultimately, we will want to have a distribution of the models and also recognize that a priori models are more likely than others.
That's funny about having a flat prior over models. It's almost like return of the frequentism. All models within this class are equally likely. So that's the special case of Bayesianism, where it sort of anachronistically is frequentist again, because then you're selecting the maximum likelihood model structure, or weighting model reliance in a portfolio on its maximum likelihood estimation. But then rather than using an ML value, the model itself is actually engaging in a Bayesian inference process. How about representations of uncertainty within the model, like just taking a given architecture as fixed, I'm curious about how are uncertainties represented? There was some discussion of lossless and lossy compression. And do we have any way to have interpretability of the uncertainties across layers? Like, do you find that you can trace those state estimations and uncertainty estimates and they ring true? Or once we're past the pixel level, is through the SVD and all of this, are we already in spaces that are not human semantically interpretable?
Good question. So, yeah, coming back to one of the points that Arun made, because we do this SVD and we throw away some like less relevant components, we are throwing away information, and so we're always in this lossy compression kind of setting. Now, what we've done in this paper and also in other experiments is to just try to reconstruct expert play or any other kind of video or agent from the RGM, and usually it works pretty well. So as you can see with the Dove or with many other examples, the RGM does a good job at compressing and reconstructing, but we haven't actually looked into mechanistic interpretability of like this state in the RGM actually encodes this, and this state in the RGM actually encodes that. So that would be interesting to look into.
I think in the MNIST example, there is a little section where it said like, okay, at the very top level, we say there's basically a value per class of digit, which feels very much like, okay, in the intermediate stuff, it's very uninterpretable, but at the end, we're going to have, okay, we're going to say each of these values at the top level can have corresponds to a digit because we're designing a classifier. I think it's a really interesting question that's not just specific to this paper or to active inference. I think it's to self-supervised learning in general, which is how do you interpret that if you're learning the structure of data from the data without anything labeled? How do you get that interpretability? I don't think there's an easy answer to that.
Yeah. Like, so here at level 4. Okay, so this also notes the matrices in this figure are not simple likelihood mappings. They're concatenated likelihood mappings from all hidden states at one level to all hidden states and paths at the subordinate level, where the sum to one constraint is applied to states each child could be in. So we're taking some higher level path trajectory and pulling lower level observations from a probability distribution, sum to one at that lower level for the child. So here at the top level, there's 10 states. So it's almost like if you came across an alien handwritten text, how would you know how many letters there were? Or if there were several writers with different styles, how would you say how many discrete symbols? Because that's kind of like this unstructured or semi-structured learning question. You have cursive handwriting from a language where you don't know how many discrete symbols there are. So you know there's a discrete compositionality at the level of the word, let's just say. However, you're getting the raw data, and then the pixels to planning in the linguistic case, or the phonemes to planning, is like, how do you go from a continuous visual or sound data to inference and planning over language production? But then you don't know how many discrete elements to have per se. But if you can have if you can be making a domain-specific model, that may not be a relevant question. You may just be able to say, we know we're going to get to 10. Find me the best 10. But it's interesting that the compositionality of the RGM could extend to higher orders of structure, with the trade-off that there's just more and more as you continue to expand how many states there can be. It doesn't escape the curse of dimensionality. It's like swimming in the curse of dimensionality, or casting the spell of the curse of dimensionality, but at least in a way where the model architecture is going to be able to be implemented using the inference methods that are the same across different scales.
Quick question on that. Do we think that the PCA part of this could give you a clue as to how many values a particular state could have in a layer? If you said, I think, Daniel, you had this idea in the 0.0 of saying, well, maybe we just have as many values a state could occupy that explains 80% of the variance at that level. So then you could say, then, I mean, we're sort of moving the complexity from this part into construction of the training data, which we should definitely talk about at some point on this call. But you could then say, yeah, exactly. That's the graph that I wanted. If we're going to just a priori say, I only need to explain 80% of the variance on this stuff, chuck some training data at it, and then we say, this training data had like 10 digits, and then you basically end up picking 10 values because that explains enough variance in the training data to do a good enough job.
Yeah, for sure. And I would say that's also implicitly what happens when we're optimizing model free energy, right? Because we're trading off accuracy and complexity. And what you're mentioning may be like a more deliberate way of saying, well, we have this target. What is the minimally complex model to achieve this accuracy target, for example? And yeah, that would be super cool to do. I think specifically for more like engineering and industry applications, that would be something that people would be very interested in, because, for example, regulators, they don't talk in terms of, oh, your free energy should have lower than this value, and then you can use your model for self-driving cars, right? You're approved. It's more like, oh, want some kind of accuracy or some kind of explanation of some data about a certain threshold, and yeah, it would be very worthwhile for this kind of application.
Yeah, how to convert from a sort of model intrinsic currency, the way that different structural models are compared with each other, or the way that alternative parameterizations are compared within the same active inference model through comparison of their free energy values, how to convert that into a value or a currency that matters, like an actual risk profile or a cost or a time estimate. That's the critical question. How does the reliability of the inference translate what would be an interesting way to go, Lance? And then for those in the live chat, please feel free to write some specific questions and I'll ask.
Sorry, specific interesting way to go for what?
Or just what do you feel like we should continue with? Or
oh yeah, okay.
How do others pick up and continue with this work beyond studying the background 11 and a half PhDs needed to continue with this, knowing that better and more advanced open source tools are under active development here and elsewhere? But I mean, what's the way to engage with this material with the current state, or what are your next plans for how it continues from this preprint form?
Yeah, so good question. I think there's already a lot of ideas that have come up in this goal. I think one interesting idea is what Arun mentioned, like using tools from machine learning to improve generalizability in RGMs. More broadly, my personal take-home message, because we've been talking a lot about well, first of all, how RGMs work, but also what their limitations are. So this is my understanding is that this is a very new kind of model, and there are a lot of limitations. But there is the really cool thing about this paper, and this is why I'm personally excited about RGMs, is this universality claim. The fact that RGMs are super expressive. You have this like one architecture that can learn many things that are pixel based, as we've seen in the paper. And so this is what we've seen empirically here and in other places. Then there's the more theoretical reasons for why that's the case. And I would say that's more of a physics question of like understanding renormalizing groups and why the world may be or may not be renormalizable to some extent. So I think it would be super cool from a theoretical perspective to have a better understanding of that. From an applied perspective, so we've seen all of these limitations, and it was already clear on this call that for each of these limitations, we don't know exactly whether it's a fundamental limitation, whether the limitation lies from the current implementation, or maybe from the current instance of RGMs, but we can modify them in some clever way to actually overcome the limitation. So there's many different places where improvements could come. Code, the actual structure of the thing, or maybe even the theory. Maybe we need more than renormalizing generative models. Maybe renormalization is not all you need something else. So at the moment, I think we should be, looking at where each of those limitations are, and how to go forward from there. The other thing is classical active inference, like the discrete planning, does actual planning. It plans multiple steps ahead, and it has this counterfactual aspect. In RGMs, you don't have that. You just learn the transitions from state to state at each level, and then you infer them from the data. So you're like in this self-fulfilling prophecy mode where you've seen your training data and you're reproducing that from the RGM. And it would be cool to know if you can combine the strength of classical active inference and the RGMs to have some planning at one or multiple levels, some actual planning with information gain to actually help this generalization aspect by improving the model with some new relevant data. So there's many directions this work could be taken in. Personally, the direction that I'm most excited in is this idea of model uncertainty, because a big question in machine learning and also developmental cognitive science is this idea of structured learning. How do you learn the structure of a model of the world? Now, there's a lot of papers, evidence, and I think there's also a lot of debate, but one interesting paradigm is this idea of model inference. And the way we've been thinking about structured learning and active inference so far is about optimizing model free energy. So we take the model that has the lowest free energy. When we do that, we are Bayesian in the states and parameters, but we are frequentist in the model. And that goes exactly to what we were saying before, this idea that you have this flat prior and you're doing maximum a posteriori estimation. And so we know that being frequentist is fine, but you can this means that you can overfit. It means, basically you're selecting the model structure that overfits, that best fits the data and which may overfit. You're not recognizing any kind of uncertainty. And there's actually a lot of theorems that show that with limited data, but even unlimited data, there's many instances where multiple models could explain the data equally well, which means that they would have the same free energy. Now, which one do you pick? And two different models could yield two different decisions. So if you're in a real world scenario, one model may be, the true model or what we want the agent to have. The other one would be wrong and could have some, unsafe decisions being made down the line. So what we want to be moving to is this idea of full model inference, not just map estimation, but actually having a full posterior over models. And this would be, for example, a particle approximate posterior where you're entertaining a mixture of models. And so basically it means that you would be doing Bayesian model averaging for all of your predictions. And yeah, so we want to be moving towards that, in my opinion. And what this affords, which I think is super important, is so when you have this uncertainty about models, you have this idea of taking actions that maximize the expected information gain about your model. And so now you can start to learn your model in a self-supervised way, and hopefully in a way that also generalizes, because you're making this epistemic search that informs your model, which we're currently not doing. At the moment, we're seeking data that's informative for the states and parameters, and we're overfitting the model, and we want to be moving beyond that.
Awesome. Yeah, very interesting. It's like equivalent to only doing policy selection on pragmatic value is just utility seeking. So then if the utility of the modeler is model fit, they have entered into a pragmatic only analytic mode that in single-minded pursuit of what appears to be a totally valid, defensible analytic goal of accuracy or of data posteriori fit, ironically produces local overfitting. So it's like exactly why we use expected free energy for policy inference, because it does have the epistemic value component. And then now with this level among portfolios of models, it's like we need to remember why we put the epistemic value into the architecture at the base layer, because it isn't enough to just have the epistemics at the base layer and then forget about it at the modeler's level. There's actually a role for the epistemic value and also for the lifelong learning. Whereas in the examples here, there was a training phase and then a test phase, as opposed to like sleep-wake type train and test and updating with online inference, like if the rules of the game changed or something like that.
Yeah, totally. Yeah, so you want to be able to handle environments. So let's say, going back to games, because I guess we love games, but it doesn't have to be games. Let's say you're in an environment, and you learn how to play the environment, you learn the generative model, and then you get to the end of the level, you get to a new level, and the environment changes somehow. The number of categories changes and so forth. You want to be able to handle that in a graceful way. And you want to be able to handle the inherent uncertainty about the world. So there's a lot of work on AI-driven scientific discovery. And you can argue that, I mean, science is about understanding the mechanisms that generate the data that we have. and in particular the mechanisms of cause and consequence, right? What causes what among our latent states. So this is like a totally, like an example that all of us can relate of the fact that we have uncertainty about causal structure. And we may also have uncertainty about the number of representations used to explain a particular data set. So let's say I'm a young child, or I'm a zoologist and I'm in the forest and I see an animal I've never seen before. Is that animal part of an existing species that I know? Or is it part of a totally new species? And there's two hypotheses. At this moment, I don't have enough data to decide between either of them. I'm going to conduct, as a scientist, experiments. Well, just going back a little bit, it means that I have a posterior with two different models that are equally likely or somewhat likely. And then I'm going to conduct an experiment to decide whether this animal is part of an existing or new species, which means that to do that, I need to have some notion of what would happen if I did that, like information gain about the model that I'm using about the world. So this is like a super simple example of like we fundamentally need that in a biomimetic agenda of like creating agents that, you know, resemble us and modeling and so forth. Also from a statistical perspective of like not overfitting. But it's like pretty hard to do in practice.
How about coming back to one of Arun's questions? In what ways is time a special dimension? We talk about planning through time, and that's intuitive. From a folk psychological perspective, how does the model handle time similarly or differently? About RGMs or just in general? I mean, what is time? How is it being treated similarly or differently to other dimensions?
Yeah, good question. I think it's a very fundamental and also physical question. But just in terms, I mean, very, very simply in terms of the model, time is the only direction that we can control. It's the only, I mean, we can't control the flow of time, but we can control the evolution through state space as time unfolds, and those are actions. Now, one interesting thing about the paper is that we not only renormalize in space, in state space, but we renormalize in time. And so we have this, in the current architecture, this one step ahead actions at each level, time horizon of 1. It could also be 2 or 4 or whichever you want, as long as it is the same as at each level. But yeah, the point is we renormalize both in space and time. And I think this would be a good question for Karl of like, why is it important to renormalize both in space and time? I don't really have a sense for why that is, but he probably has a very compelling reason for why that is.
So I'll give a little bit of detail as to why I asked the question. So there's a very technical reason, and then there's like a wider reason. The very technical reason is to do with the overlapping part that we talked about before. And I noticed in the paper there doesn't seem to be overlapping time sort of factors. You go from one state above to generates the initial state at the level below, and then a transition. And then you do the next pair. But the pair of observations at the level below don't overlap. Whereas in the MNIST example, you had, there were radial basis functions that were like 4 pixels wide or whatever, but they overlapped, which I thought was really interesting. So that was the very technical reason why I asked, oh, is time separate here, where the pairs don't overlap as you're doing the renormalization? But I think the wider question of why it's interesting is that I don't really understand how you would plan with respect to space. But as you say, like with time, it's the rollout. That's the critical dimension of you go, if I do this, then in the future something happens. But my brain doesn't compute what planning would look like in space. But yeah, we'll definitely ask Karl in the .2 and probably be just as confused at the end. But
That kind of makes
Or
me
even
think of
more.
a wave propagating out, like in a game of life situation. A wave is propagating out at one click per time step. So it's moving, it's a wavefront in space-time. From the surfer on the wave, they're not moving, but then renormalized over space, it's like, what will happen to that time step at the next time step? Well, the wave's going to hit it or it's going to leave. But from the wave's perspective, renormalizing through space-time, it's stationary. It's a stationary traveling wave that still is treating time in a little bit of a different way than space. But for all systems that we're studying in time, which basically are the natural systems, we can't really get away from it. But maybe there's like a hyper time crystal view on some of these systems that spatializes time. Okay. In some of our
Food for thought.
yeah, in some of our last pieces, again, if anyone has questions, feel free to write it. Okay. Rex asks, how has the progression been with the Atari challenge? Encouraging results?
Yeah, I mean, really good question. I'm not sure how much I'm able to share, just because of confidentiality issues. But I would say overall it's quite challenging. Definitely very interesting results. Many different approaches that are being tried because, of course, you have this RGM approach, but there's many other types of generative models that you could be exploring for solving this type of task. The really interesting deep question is what kind of structure or structures is sufficiently universal to be able to express any kind of Atari game. And the day we solve that, we'll actually have learned a great deal. At the moment, we have some leads, we have some promising results, but we are still far away from being able to solve all the games with the same structure. So I think there's a very interesting progress in terms of scaling up. But yeah, still far. And as always with these research questions, it is always hard to know, how long we'll need to actually solve the challenge.
Yeah, maybe just think of the game, how children pick up games, and Calvin Ball making up games, and what cognitive capacities support the idea. Like, maybe there's a game hanger or high-level game virtualizer that then can be like a sandbox for creating games with arbitrary structure. You're going to tell me a number that ends in a 7, and then I'm going to do this dance. It's like, that's our game. But because it's a rule set within a space, within a container that's understood, and so although generalized coordinates, RGM, and so on, in theory, can go for infinite number of dimensions for any finite system, it may only be several levels of generalization or path extraction, or just in the example of time, even with 2 time steps per level, at some point, with time doubling, you're talking about a transition that's longer than a lifetime. So it becomes a kind of an extraneous inference. And similarly, making it finer scale, you're going to quickly get to the state transitions of walking at a picosecond, which again don't really matter. But if there were either automated ways or interpretable human-in-the-loop type ways to say, okay, the SVD is looking pretty uninformative at this small scale and at this large scale. here's the bulk of the meso variance that we're working with. Here's the information content across these coarse grainings. Here's sweeping across different windows and grainings. This looks like a good graining approach. Here's where the meat is to chop up, and that relates to the focusing the computational resources on where the information content is. Focus the resources on where there's information to glean, and then truncate the model's dimensionality beyond the point of diminishing returns. Like it goes without saying, / is hard to say sometimes, but that's an extremely different paradigm for fitting small to very large models than coming with a fixed number of parameters of a large model and a fixed data set as much as you can, and then colliding the two until you can optimally reproduce the training data. While there is this element of parameterizing it on training data, in principle, you can just specify generative models and generate synthetic data. We do this all the time for different models. You don't have to train them on anything. You can just make a thermometer in a synthetic room and just let it play. So it's just interesting how with these new Lego toolkits and new composabilities that can deal with data and play in that sort of empirical test train mode, but they also lend themselves to a lot more dynamic reconfiguring that I think is the main piece we've been wrestling with, which is it gives us more affordances in building and modulating these models, but every degree of freedom in the modeler's toolkit is double-edged because it expands the combinatorics of what is possible, possibly diminishing the proportion of good solutions, but maybe those good solutions get better and better, though they're rarer and rarer.
Just want to come in on a quick point, which I think you talked about at the very high scale, nothing really happens across, beyond a lifetime at the very small scale. You don't want to consider walking on picoseconds. From a practical point of view, I guess that's going to be very limited by your training data. So, for example, on the spatial point of view, it's what does a pixel mean in your training data? And presumably you have to normalize across all your different samples to be a pixel means the same distance in an image regardless, potentially. Or do you have to do some sort of pre-processing to mean that you're only ever taking data from the same pictures from the same camera at the same distance for that to mean the same thing across the different bits of your data? Or if they are different, does your model then have to learn that from a structural point of view? And then going on the time one, I think that's also quite interesting. Maybe it's another reason why it's different. If you're introducing videos of different lengths. So if you say, okay, here's some data where in this particular video, it's 100 frames, and this one is 200 frames. There's different levels of you're limited in how far up you can go if you're just going to continually pair and pair and pair if you've only got 100 frames compared to 200 frames. So there could be very practical considerations here for the number of levels you can have and how, what timescale you can operate on. But then also I think it does beg the question at the very top level, if you've only got let's say for the music example in this paper, if you've got a length of music and it breaks it down, like it was jazz music, and you break it down to notes and bars, and potentially you could go up to a movement, but you can only go up to the maximum level, length of your a piece of music that you're exposing in the training data. You can't go a level above that, and that sort of highest level thing could only really have one value, so you might as well get rid of it. So there's there might be some redundancy at the very top there that you just sort of can always implicitly throw away.
Yeah, I think so. I mean, and when we have the current architectures, I mean, we always show the top level as having, for example, one state or two states with a transition to another two states. But then implicitly you have this even higher level that has one state and that's static. But yeah, somehow it doesn't do anything. So, but yeah, there's many things. I guess many questions and many things that can be explored. The other thing, another question that I have is, so intuitively, let's say we're thinking, okay, I need to go to work. I need to take a certain amount of actions to go to work. Intuitively, when we plan in that setting, there's several actions that happen at the same level, or arguably, maybe not everybody's like this, but it's like, oh, I need to go down, I need to, take my car, and then I need to go up the elevator at the workplace and so forth. It seems that this plan maybe happens at the same level of abstraction, or like there's many cases where we plan at the same level of abstraction. And in the current RGM architecture, we just have one step ahead, or like a fixed amount of steps ahead that are reproduced at each level. So yeah, I mean, you can definitely reproduce the example that I talked about by saying, okay, well, we're going to plan, 10 steps ahead at each level, and then it would fit with more complex plans. But, how can we allow some flexibility there? Or is there some flexibility that we need for the time horizon at each level? Should it be different from one level to another and so forth?
Yeah. Well, it's like the controls in the studio are being explored and fleshed out because you could sweep across different planning horizons, or you could plan for the same amount across horizons. Like, just like it's brought up with when it's connected to the convolutional neural network. It talks about how the special case where the likelihood mappings are conserved over groups, one has the discrete homologue of convolutional neural network. So if you're just trying to make the best single filter to pass over an image, you have a CNN. Whereas if you open it up to different locations of the image having different filters, that's the blessing and the curse. Now you have that many times larger of a state space, but for problems that have that statistical structure, that would be the way to go. So that's what motivates this meta-modeling question of how would we recognize whether we're in a situation where single filter is better than n number of filters. Like, these are where the modeling questions quickly rise in a way, because where our inference hits the metal, we know how that's going to happen in terms of Bayesian graphical model and variational free energy. It's just how to know what level of abstraction to enter into the problem, and really what's the purpose of the model. Because it's really easy to set up a situation where for example, policy inference is a slam dunk. And it's easy to set up situations where the policy inference is hopeless by design. So what is that sort of Goldilocks zone where if you could curate only the expert gameplay examples and do resemblance modeling, but if you already knew who was expert, then you already have those traces. So it's like it's interesting how with a strong floor and grounded in a really low level way to balance accuracy and complexity, we really quickly hit these data science questions about what the analysis is for and what structure the model should be taking on. Okay, in our last minutes, okay, another question. Are any other benchmarks being looked at, or just what kinds of benchmarks do you think for the open source community would be interesting for us to pursue?
With active inferencing and with RGMs. So with RGMs, I mean, there's several things, right? So there could be imitation learning benchmarks. I think this would be very interesting to go into, because arguably this isn't, I mean, the current state of RGMs, it's an imitation learning tool. It's not really a planning tool. It's also a compression tool. In terms of, so there's Atari, but arguably, if we really want to solve Atari, we want to put a planner in the RGM. So we don't want to be able to learn necessarily from expert data. We want to learn in a self-supervised way. And so there are various things that we're exploring there, extensions of RGMs in various ways. And then, you know, I mean, there's so many benchmarks out there. One thing that's interesting for going to Atari is mini Atari. And then there's all of the robotic benchmarks that I think are quite interesting. I mean, you probably know many other interesting examples, but yeah, I think these are the most interesting ones, at least from my perspective. It also depends on the feature that you're developing, right? So maybe RGMs are particularly good for imitation learning. But if you're in multi-agent active inference, then you probably want to look at multi-agent games or things that require cooperation to solve certain types of problems. I would say it's very much open-ended and depending on the strength of the particular approach.
Okay, what are your next moves? I mean, how will your year proceed, and what are you excited for?
So I'm super excited about this model uncertainty thing. This idea of how do we do Bayesian inference over models in a way that's fast enough so that we can plan to take actions that improve our model over time. And this is also interesting, I guess, from bridging multiple fields together. Because when we look at, for example, the work in computational cognitive science by folks like Josh Tenenbaum, Sam Gershman, they think very much in terms of inferring the model of the world, having a distribution over models of the world. It's not something that we're doing, again, at the moment, and I think this is a limitation. When you look at other folks like Yoshua Bengio, who are interested in AI safety and also AI-driven scientific discovery, they also have this uncertainty about models and this Bayesian inference, which is very important and interesting. So then when you accept that this is the way that things need to be done, then there's the question of how do you do the Bayesian inference in practice? And there's a wide set of tools for doing approximate inference over models. It's still a relatively young field, so there's lots of improvements to be done there, lots of hardcore statistics and machine learning, very deep questions. So this is like one direction that I think is interesting to pursue. And then once you have that working well. And by working well, I mean you want a method that's able to infer models very fast. It doesn't need to be super accurate. When you think about humans, we typically only have, a few hypotheses about the causal structure of something or something in the world. So we don't necessarily need to have a super complex approximate posterior of models. Also, that would be very computationally complex. So we want to look for things that are fast and that operate online. And so once you have these kind of methods for inference about a model, then putting that into an agent and having the agent learn de novo, in a self-supervised way, in its environment. And the other challenge for that is because you're doing model inference, there's no, it's not, strictly speaking, it's not model growing or pruning anymore. You're just doing model inference. So your space of models is fixed from the outset. And so therefore, if you want developmental agents or lifelong learning agents, you want a space of models that can pretty much explain anything the agent would ever encounter. Or you want a space of models that is able to express anything that the agent would need to survive. So you don't necessarily want something that's Turing complete, but you want something that's, a class of models that's pretty expressive. But it should also be sufficiently coarse that you're able to do efficient inference on it. So you have this trade-off, which is very difficult to navigate, of trying to find a class of models that is universal in some sense, but also sufficiently coarse that you can, do things manageably. And I think this is where RGMs can potentially be very fruitful, because they are very expressive and they're also, they have very powerful inductive biases, this like renormalisation aspect that makes your model space a lot smaller than it would be with other methods. So this, this is one way forward I'm like particularly excited about.
Cool. Yeah, expert learning is kind of the inductive side, and then the creativity and the abduction, and being able to jump to an adjacent possible from what has been induced. That's exciting. Arun? And then we'll kind of have our last thoughts here.
I thought that all of those directions of future research sound really interesting. I had a very possibly silly question, which is on when we're talking about learning about structure, are we also learning about potential new actions that an agent could take? And I think that ties in with the AI safety part quite nicely of currently in active inference, if you come up with your own generative model, as the modeler, I can say, these are the actions available to my agent. It can only do these things. It has to pick one of those things, and it can't do anything else. But if we're going to learn online about possible actions, like new actions I could take, suddenly now I have learned that I have the choice to drive a car, whereas before I could only walk, then suddenly the range of impacts that I could have, me as the agent can have on the world massively increases and is possibly not predicted by the modeler at the time they're creating their agent. So I think that, my question is sort of about what type of structure do we want to learn with these new models? And does that include actions that an agent could take?
Yeah, really interesting question. And so I'll give you a couple of thoughts. There is a Toby Sinclair Smith, which you've probably had here on the show. He does category theory, and his latest formulation of structure learning, active inference with category theory, he talks about blankets that change over time. And so this would be this idea of adding, removing actions of observations. So I think that's interesting, and he would probably have some really cool thoughts about that. The other perspective is let's say you fix the observation space and the action space. And let's suppose that I, as a person, exist only in a small part of my head, and my observations and actions are the information that's coming in and out of this small part of the head. Now, when you're a baby, you don't know that you can act on your body, right? So you don't know that your foot is you and your arm is you, but you're gonna learn eventually that there is a very precise mapping from the information that's coming out of your action neuron to what your arm can do. And so eventually, even though your arm is a latent state, you're going to associate moving my arm with an action that you're taking, because there is a very precise mapping from your neuron to what the arm does. And I think this would be, this would basically, when you think about it this way, there is maybe a lot of actions that we can lump into the latent states of the environment, that we have direct, very precise control over. That's the way I'm thinking about things.
Yeah, that's the babbling. It's interesting. I'm also just thinking of expert video of figure skating, but then that doesn't mean it's safe for a non-expert, or there could have been a body position that was safely reached, but then if a different object in a different context so there's so many interesting fundamental issues, and that is the sort of benchmark and reproducibility question, is how can we compare models with these radically different forms, possibly in the future also radically different substrates, solving these problems in different ways, such that the ways that benchmarks are even conceptualized in terms of like CPU or RAM may only be a constrained way to think about how some of these embodied problems are solved. Lance, thank you for this, and all the authors for the work. We're very excited to talk with Karl and others in 58.2 during the Applied Active Inference Symposium. So, good luck with your works. See you next time.
Thank you so much.
Thanks, everyone.